This is Numbers with Nicole, and we're going to do another lesson in our circle unit today, and we're going to be talking about tangents that are drawn to a circle. So a tangent is a line or a segment that intersects a circle only once, and that is at the point of tangency. So here AB is a line that is tangent to circle C. Remember, circles are named for their center. And AB, line AB, only touches the circle at point A, so that would be the point of tangency, point A. There should only be one point of tangency because a tangent only touches a circle one time. And then if we take a part of that tangent, that would be a tangent segment, but that segment should include the point of tangency. Another thing to keep in mind as we look at these tangents, so here would be our tangent, is that we will also be talking about the relationship with the tangent and the radius. So here we have a radius drawn from a center to one point on the edge of the circle. And then here's another radius. And we know that radii of the same circle are equal in length. So this radius is equal to this radius, equal to any other radius that we draw in this circle. So let's kind of just apply the vocabulary that we have here. We're going to name the circle. So this would be circle C, named for its center. We want to identify any radii, so those are segments drawn from the center to the edge. So AC is a radius, CD is a radius, or DC or CA, and we know that those radii are equal because they are drawn in the same circle. We don't have any other radii drawn. We could connect C to F, and that would make another radius. We're not going to do that here, but that would be one that if it was drawn. Diameter is a segment that extends from one end of the circle to the other through the center. So our only diameter here is ACD, or you can call that AD, or DA. Right, that's the only one that we have. We do have BH is another segment in the circle here, but that doesn't pass through the center. That would just be called a chord. So now we're going to identify any tangents. So tangents are our new word, and those are lines or segments that only touch the circle once. Tangent is a touch, right? So if you only touch something, it's once, right? So not more than once. So only touch once. And so what segments here only touch the circle one time? That would be GF, right? If it continued infinitely, then that would be another segment. And FE. Those could be considered one line, so we could call that segment GFE. And F would be our point of tangency. And points are only named with one letter. So our tangents is really only one tangent, because these are the same line, FE and GF. And now the other thing we're going to talk about with tangents in this lesson is if two tangents are drawn from the same outer point, so here we're going to call that point B, and they are drawn to the same circle, so AB is a tangent to circle O, BC is a tangent to circle O, they only touch the circle once. If that is true, so they're both drawn from B, they're drawn to the same circle, they're both tangents, so that means that those two would be equal or congruent to one another. So if AB is 6, then BC would also be 6. So we're going to apply this. AB is tangent to circle C at B, and AD is tangent to circle C at D. So what does that tell us? That tells us that these two tangent lines are equal to one another in length because they are both drawn to the same circle C from the same point A. So we know AD is equal to AB, and using that information, we can set up an equation. So we've applied the geometry to write an algebraic equation to solve for that value of x. If they just asked us what AD is, we would be done because we know they both have to equal 11. So we're going to use algebra, our inverse operations, to isolate the x and get it by itself. And the opposite of multiplying by 2 is dividing by 2. So we get that x is equal to 4 for our first example. Right. So when a tangent and a radius intersect, they are perpendicular, meaning that they form 90-degree angles. Form 90-degree angle at that point of tangency, or the point where the radius and the tangent intersect. And remember, that should only be one point. And so in these two purple boxes here, all that means is if we have a tangent and a radius meet, then we know that there is a right angle there. And if we know that there's a right angle there, then we know that whatever that segment is that intersects the circle once must be a tangent. So it goes both ways. If we know one, then we know the other. So in this picture below, we have AB is 5, BC is 12, and all of AC is 13. And we want to know, is BC tangent to circle A? If BC is tangent, then what would be true? Well, then there would be a 90-degree angle at angle B, making this a right triangle. And if this is a right triangle, then all the sides of any right triangle must satisfy Pythagorean theorem. So 5 squared plus 12 squared, does that equal 13 squared? That is the question. And so if we get that that is true, okay, so we get 169 for this side, and 13 squared we also know is 169. So since Pythagorean theorem is met, then there must be a right angle, because these sides represent the sides of a right triangle. So yes, BC is a tangent, because we have shown that there must be a right angle here, and this must be a right triangle. Yes, BC is a tangent, because that's the relationship. This radius AB and this tangent BC have to form a right angle if it's a tangent and this is a radius. So find the measure of angle C. We're going to do a little bit of review here. Find the measure of angle C to the nearest whole degree. So now this is angle C, which is what I want to know. Okay, now we have a right triangle, and I want to find the angle, and I don't know the other angle A. So we can use trigonometry, and you can use any of your acronyms, SO, CA, or TOA. I'm going to use sine, which is, so sine of the angle that I'm looking for, which is C, would be the opposite side 5 over the hypotenuse 13. And since we're using the since we want to find the angle, we're going to use the arc sine, which all that means is in our calculator, we're going to hit the second sine button. 5 divided by 13. That is, to the nearest whole degree, 23 degrees. If we had angle A, then we would just subtract 180 minus angle A minus 90 degrees, and that would leave us with angle C. Right, we're going to do one more example, kind of tie all this information together. And then there's one other one that we might do after. Let's see. All right, so CD and CB are tangent to circle A. So from the same point to the same circle, I know those are going to be equal. And we have a radius is 12 millimeters, and they told me that BC is 16. So I also know that CD is 16, based on these being both tangent to the same circle from the same outer point. So they want us to find in part A, AD. So if I draw AD, that's a radius. AD is a radius, and they told us that the radius is 12. And I'm going to draw another radius, AB, and I'm also going to label that 12. Only makes sense, right? So now we're going to find CD, which I've already labeled on the picture based on what they gave me at the beginning. So CD is going to be 16 because CB is 16 and tangent to the same circle from the same point. From same outer point C. And that's what the theorem is, right? That's what the theorem says. So now, Now we want to find the length of AC. Woo, I'm going to draw this segment AC in. How am I going to find that? Well, I have a radius and a tangent that meet at a point of tangency B and D, and so that means that those must be right angles. So if I have a right triangle with two sides and I want the third side, then we know that we can use Pythagorean theorem. And so I'm looking for AC, which is the hypotenuse of either of these right triangles here, either the top one or the bottom one. So I'm going to have 12 squared plus 16 squared equals C squared. 12 squared plus 16 squared is 400 equals C squared. The opposite of squaring is taking a square root. And we know that that's going to be 20 for AC. And lastly, if we had another question, not lastly, because there's a last part here. Let's see. So the area of triangle ACD. So area of a triangle is 1/2 base times height, where the base and the height, or the numbers that you use, have to be perpendicular. Okay, so that's 1/2 of 16 times 12. And that is 96 square units. Oh, they gave us millimeters, didn't they? So let's make that millimeters. Millimeters. Can triangle ABC be proven congruent to triangle ADC? Yes. All right, so that goes back to our methods. Could we use side, side, side? Yes. Could we use side, angle, side? Yes. Could we use hypotenuse, leg? Yes. So we have lots of methods that we could show based on what we know about these relationships and the values that we were given. So we could use hypotenuse, leg, side, angle, side, 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 side. If you found the angles using trigonometry, you could use angle, side, or angle, angle, side. Remember, angle, angle is not a valid congruency method.